Here we're going to talk about the derivative of the secondary trig functions and the inverse trig functions. We're going to start off with the inverse trig functions here. So by arc sine, arc cos, and arctan, recall what I mean by that is actually arc sine of x is actually just sine inverse of x. Same with arc cos, it's just cos inverse of x. And arctan x is just tan inverse of x. Remember, the reason why we like to use this notation, arc sine, arc cos, and arctan, instead of the little -1, is because the little -1, although it does stand for inverse, it can also stand for reciprocal, which can be a little bit confusing. So in order to get rid of that confusion, we're just going to use arc sine, arc cos, and arctan. So the patterns here for those are given right here. So the derivative of arc sine, we're not going to go into the derivation of those of these tools right now. We're just going to look at how they work and how to apply them. So the derivative of arc sine, so inverse sine, is equal to this, 1 over the square root of 1 minus x squared. The derivative of arc cos is negative 1 over the square root of 1 minus x squared. So notice it's the same thing, just with a negative in front. If you're wondering why that is, you can actually think about the graphs of these two things, and it should actually make some sense to you why it is. Arctan is even simpler, actually, 1 over 1 plus x squared. These are three things you should memorize. And really all you have to do to memorize them is you have to memorize this pattern. Remember that sine is the positive one, cos is the negative one, and then tan is just sort of 1 over 1 plus x squared. It's a little bit simpler. Now, one other thing to keep in mind, I did make a mistake here. If you look at the Leibniz notation, arc sine x, arc cos x, this should be arc tan x. That is a mistake right there, so please correct that. Okay, so let's see how to actually use these things. Feel free to pause the video here and try these yourself, actually, before I even do them. I think you could probably handle them. So starting off with the first one, 1a, 2 arc cos x. Well, there's nothing really special about this one, right? We know when we have a constant, we can sort of pull that out of the derivative and leave it out in front. So it's just going to be 2 times the derivative of arc cos x. And if we look at the top, our derivative of arc cos x is just, I'm going to put it all in brackets, negative 1 over root 1 minus x squared. And close the bracket. That's it. That's all there is to it. We could simplify it by multiplying that 2 by that -1, just to make it a little bit simpler and put that in the numerator. But really, that's all there is to it. Oops, 1 minus x squared. That's all there is to it. Okay, let's look at the next one. Negative arctan of 2x minus 5. So this one, we should realize we have a function within a function. And we also have this negative sign in front. The negative sign in front is similar to the 2 in the previous one. We can just pull that out of the derivative, so we don't really have to worry about that part. Now, when we have a function inside another function, so 2x minus 5 is a linear function inside of arctan, the first thing that should go off in your mind is chain rule. So again, to use the chain rule, we're going to do derivative of the outside function times essentially the derivative of the inside function. So in order to do that, the derivative of arctan of something is just 1 over 1 plus x squared. Now, instead of the x, what we actually have is this 2x minus 5 squared, right? So it's like I just replaced this x here with the 2x minus 5, the thing inside the arctan. And then we have to multiply at the end by the derivative of the thing inside, which the derivative of 2x minus 5 is just 2. That's all there is to it. Again, we could simplify. We could bring the 2 to the top, make it negative. We could simplify what's down here, but we've taken the derivative. So I'm actually going to just stop it here because we have done what we set out to do. So for these two questions, again, I'm going to strongly encourage you to pause the video here, try these yourself. That's where the best learning will happen, where you try these yourself. Even if you don't get the right answer, I'll go through the right answer so you can check your answer after you've tried them. Okay, so let's go through them together. This one right here, very similar to the previous one where we have a function inside of the arc secant, or sorry, the arc sine. So what we're going to do, g prime of x is just going to equal, I've actually been really bad about notation here. I should be putting, really bad about notation. This should be an f prime of x right here, right? And this one over here, a, should be y prime. That's the derivative, right? I don't know why I didn't do that. That's a little bit silly. Sorry about that. Okay, going back to this question. G prime of x. So we're going to pull that 2 out of the derivative and then take the derivative of the outside function, which is arc sine. The derivative of arc sine is the positive one, right? 1 over the square root of, I just need to double check. 1 minus x squared. Nothing wrong with double checking. 1 minus x squared. Oh, but it's not x squared. Because what the x is, it's not actually an x. It's like this chunk in here, right? So it's that squared. So it's 3x squared. And that's all under the square root sign like that. And then we have to multiply, according to the chain rule, we have to multiply by the derivative of what's on the inside, which is 6x. There we go. Again, we don't have to simplify there. That is the answer. And D, we have h of x. So h prime of x is going to be what? Well, this is a case where we actually have two functions essentially multiplying by each other. Two things with x's in them multiplying by each other. So the little bell that should go off in your head should be product rule. So derivative of the first part times the second part plus the first part times the derivative of the second part, right? So the derivative of x squared is just 2x, and then we're going to multiply by arc cos x squared. We don't do anything to that part there. And then we have to, add the first part times the derivative of the second part. And the derivative of arc cos x squared, we know, is 1 over, actually negative 1 over the square root of 1 minus x squared. And x squared is x squared squared, right? Because that's the inside function, multiplied by the derivative of the inside function, which is 2x. There we go. Not the prettiest derivative, but that is the derivative of that function. Okay, so now that we're okay with the derivative of the inverse trig functions, let's look at the reciprocal trig functions. So we want to know what the derivative of secant x, cosecant x, and cotangent x, as well as the inverse versions of those, right? Arc secant x, arc cosecant x, and arc cotangent x. So let's start off with just the derivative of these three things at the top. Now, we can actually look up what these derivatives are in a table. At the beginning of your textbook or the end of your textbook or something, there will be a list of a bunch of common derivatives, and these will be on there. But if you know the derivatives of sine, cos, and tangent in the previous lesson, you actually can just figure out what these three derivatives are. Because remember, what is secant actually? Secant is actually just 1 over cos x, right? Cosecant is just 1 over sine x. Notice I'm not taking the derivative yet, I'm just rewriting these functions. And then this one is 1 over tan x. So if you know the derivative of cosine, sine, and tan, you can just figure these out. This is another place where I'm going to ask you to pause. See if you can figure out what the derivative of those three things are, just with what you already know. Okay, if you're stuck or if you've already found the answers, let's just go through it together. So I'm going to actually rewrite this as cos x to the -1. And this, again, is why we don't like using that cos -1 of x as our inverse. Sorry, as our inverse cos, because this -1 actually just means reciprocal, right? When we write it like that, we can essentially just use the chain rule, right? To use the chain rule on this thing, we would bring down that -1, reduce this value by 1, and then multiply by the derivative of what's on the inside, right? So what this would look like would be negative cos x to the power of -2 times the derivative of what's on the inside. What's the derivative of cos? It's just negative sine x. Now, that's sort of ugly. Let's simplify it in this case, because if we're just looking for a simple derivative of secant x, it might be useful to have a simpler expression than that, right? Remember what this means. So this means that this cos x goes in the denominator and it's raised to the power of 2. There's also a negative sign here and a negative sign here. Those are going to cancel out, right? Because they're being multiplied by each other, essentially. So what this is going to look like, it's going to look like sine x over cos squared x, right? When we do all that simplification. So essentially the derivative of secant x is sine x over cosecant squared x. And you can write that in many other forms. Like some people like to rewrite it as sine over cos is tan, and then you have tan x over cos x, or instead of using cos x, using secant x. But essentially any manipulation of this is the same thing. So this is the derivative of that. All right, for the other two, I'm just going to show you the answers here. So try them yourself if you haven't already and see if you can figure out what they are, because they're just going to appear in 1 second. So just by doing the same process for cosecant and cotangent, this is what you should get. Now, if you plug, as I sort of mentioned, there's other forms of these. If you plug these three things into like Wolfram alpha or something to tell you what the derivative is, it actually gives you that the derivative of secant is tan x secant x, which is a little bit simpler. The derivative of cosecant x is, what is it, negative cotangent x times cosecant x. And the derivative of cotangent of x is actually, this one simplifies a little bit nicer as well. Y prime equals negative cosecant squared x. So the way that these are sort of more common definitions of these three derivatives is because they're all in the numerator, right? There's nothing in the denominator, so it is a little bit easier to do some algebra with it. Know though, you can derive these three things just by rearranging these sort of like identities. So both essentially are acceptable. You are expected to essentially memorize these because they will come in handy. It's easier than deriving it each time. You could derive it each time if you know the derivative of sine, cos, and tan, but memorizing these three will actually make your life a lot easier down the road. So I recommend doing that. Now, before we go on to these inverse reciprocal trigonometric functions, let's actually try an example or two that just use the reciprocal ones. So I'm going to leave them there at the top of the screen so you can just see them. And let's try this question here. So g of x is equal to secant x times 3x squared. Now, the notation here is not great, but what I'm going to assume is being asked is secant x, and then that 3x squared is actually outside the secant x. That's just being multiplied by the secant x. So if that's the case, we have two things that are being multiplied, right? We have secant x as one term and 3x squared as another term. So that means we have to use the product rule. So using the product rule here, it's derivative of the first part, so derivative of secant x. And the derivative of secant x above, we see that it's the first one, right? It's tan x secant x. So that's just going to be tan x secant x times 3x squared, right? That second part doesn't change. And then we're going to take the first part times the derivative of the second part. So plus secant x times the derivative of 3x squared, which is just 6x. There we go. That's that derivative. Now for b, here we have two things that are being divided, right? When we have two things that are being divided, we're going to use the quotient rule, right? So derivative of top times the bottom minus top times the derivative of the bottom all over the bottom squared. So y prime in this case is going to be derivative of the top. So the derivative of cosecant x, as you can see at the top of your screen, is going to be negative cotangent x cosecant x. If it looks confusing to you, feel free to put a dot in between to represent multiplication. If you got too many letters in a row, it can look a little bit confusing. times the bottom, which is cotangent x, minus the top times the derivative of the bottom. And the top is cosecant x, and the derivative of the bottom, the derivative of cotangent x is negative cosecant squared x. And this is all going to be over the bottom squared, so just essentially cotangent squared x. Now you can, of course, simplify this. We have a cosecant times a cosecant squared, so that's going to be cosecant cubed. You can probably simplify this. Well, we have two cotangents and a cosecant. We could probably simplify this whole thing a little bit, but I'm not going to do that. If you want to do that yourself, you can, but this is essentially the derivative. We have successfully taken the derivative. So now what we're going to do is we're going to determine the derivative of arc secant, arc cosecant, and arc cotangent. Now the derivatives of those, I'm just going to give them to you. There are some interesting proofs for those if you are interested, but for now I'm just going to give them to you to keep things simple. So the derivative of arc secant x is just 1 over the absolute value of x times the square root of x squared minus 1. A little bit weird that it's got that absolute value function in there. The reason that it's in there is because of the shape of arc secant. We're going to go through a little bit more in class why it looks like that and the actual shape of this function, but for now it'll help just to memorize that. Arc cosecant x is actually very similar. The derivative of that is negative 1 over the absolute value of x times the square root of x squared minus 1. It's the same thing, just with a negative. Basically, the whole thing's negative. And arc cotangent is a little bit different, and the derivative of that is negative 1 over 1 plus x squared. So these actually look very similar. They should sort of trigger your memory here. If we look back over here at the derivatives of arc sine, arc cos, and arctan, they're actually very similar. They're the same essentially, except they got this absolute value of x in the bottom, and it's also switched. So sine here was the one that was positive, but cosecant is the one that corresponds to sine, right? And it was negative here. So the negative sign went from the one having to do with sine to the one having to do with, the one having to do with cosine to the one having to do with sine. So the negative sign is switched as well. So you just got to keep that in mind. But essentially what's in the denominator is the same, except it's got this absolute value of x, and it's x squared minus 1 instead of 1 minus x squared. And then the arc cotangent one is also very similar. It's just the negative version of it, right? It's the same thing, but just the negative version of it. Again, memorizing these things will make your life a lot easier. So let's go down to these last two questions here. M of x, so example 3, part C, just asks us for the derivative of 10 arc secant of 3x plus 2. So we know we can pull, if we're going to do m prime of x, we're going to pull that 10 out of the derivative and then take to the derivative of what's left. Notice how we have a function, 3x squared, inside arc secant. We know the derivative of arc secant is up here, right? So we have to use chain rule. Essentially what we're going to do is we're going to take the derivative of arc secant first, which we know is 1 over the absolute value. Now, it's not the absolute value of x, it's the absolute value of what was in the place of the x. And in this case here, it's the 3x squared. So it's the absolute value of 3x squared times the square root of 3x squared minus 1. So this is all under that square root sign, right? And then, I know we're running on to the next question here, but that's okay. Then we have to multiply, according to our chain rule, we have to multiply by the derivative of what's on the inside. The derivative of 3x squared is just 6x. So there's our derivative. Not too bad, right? In fact, this absolute value doesn't really matter much anymore when we have an x squared in there, right? Because the squared is essentially going to turn everything positive. Okay, let's, assuming we're working with the real numbers, of course. Let's go on to D. So D, Actually, it doesn't even make use of the inverse reciprocal. It's just a regular inverse trig function. So the thing that you should notice about this question is we essentially have two functions multiplied by each other, x squared and arctangent of x squared. So when we have two functions multiplied by each other, the thing that should go off in our minds is we have to use the product rule, right? So y prime, derivative of the first part, 2x, times arctan of x squared, plus the first part, which is x squared, times the derivative of the second part. So what's the derivative of arctan x? Well, we can go all the way back over here. The derivative of arctan x was 1 over 1 plus x squared. So it's 1 over 1 plus, and it's not x because we have an x squared inside there. So it's x squared times the derivative of the inside, times 2x. There we go. That's it. Again, we could simplify this, but I'm okay leaving it here because we have successfully taken the derivative. One last thing to keep in mind for these functions, there are restrictions on all of them. Look at these functions here. If we take the derivative of arc sine, arc cos, and arctan, notice how the denominator, we never want that to equal 0, right? So there is a restriction where these things x can't equal 1 here. So there are restrictions on there. And also on these, didn't mean to do that, on our reciprocal functions, it's the same thing. There are restrictions on these, right? X cannot equal 0, and also x cannot equal 1. X cannot equal 0, and x cannot equal 1. This one's okay as long as we're working with the real numbers, but there are restrictions, and that just has to do with the shape and the asymptotes involved with arc secant and arc cosecant. So just keep that in mind. If you get an undefined answer, it may be because you're trying to find the slope of a tangent where that function doesn't actually exist.